record. So, hello everybody. Today we will speak about how to build fractional order element. And this lecture continues to the lecture which we had 1 week ago. So the question is how we do it. Look, before we begin, I will repeat few words about the body, which is called body diagrams. I hope everybody knows what is this, but very short repeat is important. Before all, useful presentation of frequency characteristics was performed by American engineer Henrik Bode, and this is indeed logarithmic measure of filter gain in decibels, and you have two logarithmic axes. One logarithmic axis is for omega, and another is for gain. So if you have log-log representation, it has possibility to represent wider frequency range and wider value range. Okay. So the unit is decibel, and this here equation is very important because if you have 10 to the power of n, then the value in decibels is 20 times n. So this is good to remember. And here below in this table are some characteristic values because we will use them all the time. For example, 1 over square root of 2 is minus 3 dB, 10 is 20 dB, and so on. So you know the values. Before all, we will look how we can represent if you have transfer function, if you have S, or if you have transfer function with 1 over S. So this is something what we will look together because it is S in the numerator or S in the denominator. Here you have very simple. You put S equal J omega, and then you have alpha. This number 2, it's not important. This is we have several possibilities, and this is the second one, but it doesn't matter. Then it is 20 logarithm of omega, and because this here is logarithm of omega, then you have 20 times x. If this is x, then you have 20 times x or 20 times logarithm of omega. If it is, of course, in numerator. If it is denominator, then it's minus 20. So we can see how it looks like. If this is 0, then of course it is here 1. So logarithm of 1 is 0. So 20 times 6 is like this. So you have a slope of 20 decibels per decade. This is decade 10 to 1. Okay, this is probably what everybody knows, but it's very important to repeat. Now we go next. The phase is positive or negative p half or 90 degrees. So this is also something which is here, because why it's positive 90 degrees? J omega. What is J? J is possible to write as A to the power of J p half. So this is phi is equal to p half. Or if you have h of j omega like this, 1 over j omega, then it is omega times minus j, and this is omega times e to the minus j p half. Now here is minus p half. So this is something what everybody knows, but we have to repeat it. Now we will go faster. Just a second, let me see. Now, another important factor is the factor which is known as S plus sigma. Wait a second. Of course, we put this number 3, but again, I'm telling this number 3, it's not important. So how can we plot using body S plus sigma? Again, S equal to j omega, and then alpha, and then you see this here. We can concentrate only on the numerator, like this. So then it is h of j omega is equal to j omega plus sigma, and then absolute value we can put here, and then this is omega square plus sigma square, and so on. What is also important, you see it here on the left side, to obtain decibels, you must apply logarithm and then multiply by 20. Now, there are also two important things to notice. On the frequency range, so you have two possibility. When omega, this is sigma, which is this 0 here. When omega is smaller than sigma, and when this is this place, and when omega is larger than sigma. If omega is smaller than sigma, then this part here is dominant, this one. If omega is larger than sigma, this is when omega is smaller. If omega is larger than sigma, then this part here is dominant. And then in the first case, we have 0 dB, and in the second case, you have logarithm of omega. Of course, this, if you put here omega divided by sigma, here you will have unity. And if you have omega, then you have sigma. And if you have omega divided by sigma, then you have unity. Okay. Then we want to plot it. This is how it looks like. This black is the real one, and this dashed red line is how it looks if we make asymptotic. So now we learned how to plot body diagram of the two important, one is S and one is S plus sigma. Let me change color a little bit. Okay, what is about asymptotes of the phase characteristic? You can look at these slides, and they look like this. It's not so important. Now we come to one example. We want to plot this h of s using our body diagram, which is shortcut. So this here, s plus omega z, is divided by s plus omega pole. And you see how we can construct it. So you start here, you come to number 2, and then you go 20 dB up. And then you come to number 10, and then you go 20 dB per decade down. This is not 20 dB, 20 dB per decade. So and then you add the 20. 20 is 20 logarithm of 2. It is equal to 26. So this is how we can construct the body plot using these techniques if we look at 1, 0, and 1 pole. And this is something what we will use to construct our fractional order element. If I use MATLAB, and if I put in MATLAB such a command, body, this is the same like from the, you see here 20 or 100 times S and times 2 is 200. And then I put it in the MATLAB, you have this command. And exactly, this is exact body plot of our function which we have here. So we will use this to construct a fractional order element. Now, when we know all about body plots, we can continue with fractional elements. Before, I will clean a little bit board. Okay, now how can we obtain fractional order element? This is definition of our fractional order element. This is the basic and most important equation. If you put inside the S equal to j omega, you will have the frequency response, of course. Then it looks like this. S, so we say here, we say that j omega goes to alpha. And this is omega to alpha times j to alpha. And this is omega to alpha times e to the j p half, which is j, and then all together to alpha. And this is omega to alpha e to the j alpha e half. This is important. Okay, so this is what we have here. Of course, to obtain the magnitude, then we multiply it by f0, but it doesn't matter. So the magnitude is here, and the phase is alpha times p half. It is here, so the phase is constant. Let me see how it looks like. So if we have a positive alpha, here are 3 examples, and we have positive degrees, 30 degrees, 45, and 60 degrees. And this is magnitude, it's rising, steeper or less steep, and then we have 3 degrees, 3 examples of different alpha. Alpha is 1/2, this is the green one, of 45 degrees. Alpha is 1/3 and 2/3. And that's most important for us to notice. Also, we can have both positive and negative. This is magnitude. I had such a picture in computer, so I put the whole picture with both positive and negative. And the corresponding angles are here. You will have all these slides, so you will be able to see it. Now comes the most important part of this first explanation. There is a paper of Ostalup with figure 3. In figure 3, it is how you can use body diagram to make, for example, positive, or the same way you can make a negative angle. So how you do it? We know that if we use one pole, but 1, 0, like this. Then we go up. Then we use one pole. Then we go down, but when we add it, then we can also use another 0 and another pole. And if we try to add it to make summation, then we will have this. So this is our amplitude frequency characteristic. And if we make them very fine, then we will have something like this. So the most important things which I wanted to show you, so this is magnitude. This is h of j omega. The most important thing is what I wanted to show you, that for the realization of fractional order, we need to approximate it, we need zeros and poles. For example, like this. S plus S01, S plus S02, and so on. S plus S pole 1, S plus S pole 2, and so on. S plus S0n, S plus S pole m, doesn't matter. So here, if you go up, this is 0. Then here is pole. Then this is second 0. Then here is second pole, and so on. So zeros and pole alternate. They must be like this. So you have here pole, 0, pole, 0, pole, 0. And now, of course, depending on how you put all these poles and zeros, which are here in this impedance, then you will have a different angle here. Here you will have something like this or something like that or whatever. So you will approximately, as this red line, you will form the amplitude frequency of the fractional order element, or you will obtain the corresponding phase of the fractional order element. So this is all plot in this paper of Ostalup, and you can also not only look at the amplitude characteristic, you can also look, if you want, on the phase characteristic here, or you can look like this. But I just wanted to show you principle. Now, we remember from 1 week ago that we can design this Z of S using RC network. So we have learned 1 week ago RC networks and LC networks, but for this we don't need LC networks, we need RC networks only. But for the completeness, we learned everything. And then using RC networks, we can obtain such a curve, which is then called fractional order element characteristics. Okay. Now I will show you how we realize it. Before I start, let me introduce you my new project, which is not approved yet, but I want to have some money for the research. So the project is called, how it's called? FACSIT, Fractional Analog Electrical Circuits and Systems in Integrated Technology. Our last project was closed. It was 100,000 euros. The next one, it will be 150,000 euros. It is not big money, but it's helpful. And we will order analog devices chips, which are here, which you also have. And before, I will also introduce you to the name of our laboratory. Our laboratory is called Nanoscale Integrated Systems, which is acronym for NIS, or New Israeli Shekel, NIS Laboratory. Okay. Now let me continue with some example. What is fractional order element? So if you have a possibility to calculate current using Laplace transform in this RLC circuit, this is second order RLC circuit, then you will have a impedance of capacitance 1 over SC. This is normal capacitance. If you put excitation as step, then you calculate the current like this. This is normal Laplace transform. But if you have a fractional element like this guy here, then you will, all of a sudden, you will have Laplace to the 1/2 or Laplace to the 1.5 and so on. So we ask ourselves, what is Laplace? S to the 1/2. So the answer is, this is our fractional order element. I have realized one. This is passive. This is passive element with R and C. This was produced by my student Andro. He was soldering it. And here is the zeros and poles, pole zero plot. They have to be alternating, and then you see here how it looks like. We have measured it, our RLC meter, Agilent, and you immediately see that this guy has 60 degrees phase. Normal capacitor has 90 degrees phase. Now, I will not speak a lot about fractional order applications. You can read it when I will give you slides, so we will not waste time on it. You can see it. I will give you the slides. One important thing to mention is Cole model of bioimpedance. So this is the electrical network of the Cole model. And as you see, it possesses the fractional order capacitance. This is where the connection is between electrochemical solution and the metal. Also, I will not speak about it. We don't have enough time. It doesn't matter. It's not so important. But the basic problem to solve in circuit theory is how to calculate these elements of this such a network, and then you will have the fractional order form of the characteristic. As you see, it's this is used for pink filter, and this is 10 decibels per decade. Here are more applications. Here is the active OTA-C realization. This is element. This is my chip. I will finish soon. You will see the picture. So this is the fractional order element. It can be used to realize inductance or admittance. You have all the papers mentioned in the slides. And this is the single input version and the floating version, and this is the differential input version. This here is OTA, which we designed. It is designed using KISS approach. That means keep it simple, stupid. Now I will show you a few more pictures and then we are finished. This is a behavioral model in LT-SPICE of 30 degrees. So these here are OTs, operational transconductance amplifier, and these are capacitors. And then you can see the amplitude and phase. If you produce floating guy in cadence, then you also in cadence have 30 degrees between two sinusoidal signals. And you can, what you change only the currents. Notice these currents here and these currents here. So you use different currents and you obtain the difference transient analysis with different time lag of the two sinusoids. And then for the 60 degrees, you change the what?
There is a fractional element in a simulator like Virtuoso, or maybe Multisim. There is a.
I don't know. I think it doesn't exist. It doesn't exist. You have to put passive RC network. Okay, just a few more minutes and then we are finished. So this is for 60 degrees transient analysis. So you see the difference between the two sinusoids. And then we want to show AC analysis of 60 degrees, 30 and 45. If you change the current of this guy here, then you can have this is bias. Then you can have different values of the amplitude, but the phase is all the time the same. Magnitude you can change, the phase is the same. And then you can also look at the parasitics of the OTA. You can see how you can avoid parasitics. And then you also can produce a lossless fractional integrator. You put here capacitor, or you can analyze the influence of parasitics. And here are the equations which we use for this is very important equation for the calculation of real and imaginary part. This is differentiator. And finally, this is our chip. So this is all what I wanted to show you. I have showed you the passive and active realization of fractional order element. I showed this second part very fast, but you will have slides so you can research it as you want. So thank you very much. I don't know when this recording will stop because we have 40 minutes. Another thing which I want to say, you make any simulation in PC Spice or Simulink or whatever, then you don't have fractional order element. You can use behavioral model to define the function. Maybe I didn't try it, but I use usually RC network, which I showed you today. So this is all. I will stop the recording and we can continue with our talk.
לפי המרחק בין קווי הזווית.